Hello, my name is Steve Goodman, and I'm with the West Virginia University Institute of Technology, and I'd like to spend a few minutes talking with you about Albert Einstein's special theory of relativity. We'll begin our story back in 1861. There was a British physicist named James Clerk Maxwell who had been studying equations that people had derived many years before pertaining to electricity and magnetism. And so here are some of those equations. The terms D and E reflect the electric field, for instance. B and H refer to the magnetic field. So, for instance, this equation would help describe what happens when someone on a cold winter's day walks across a carpet, pulls up some charge onto their body, reaches out with a finger and touches a doorknob. It's a little discharge. So here, what we might have is the idea of electrostatics. In this bottom equation with J, that would correspond to a current. So we can imagine here the wires carrying a current and then making a magnetic field in the iron and surrounding space here. Now Maxwell was also very intrigued with Faraday's law. Faraday's law basically is one of the most important laws that we have for how transformers and motors operate today. Very fundamental. Maxwell is intrigued with this connection of the magnetic field changing here, making an electric field. So, but looking at these equations as they were, he felt something was missing. There was an asymmetry between the electric field and the magnetic field. So if a changing magnetic field makes an electric field, why not have a changing electric field making a magnetic field? So Maxwell added this term here. And as a result of that, right there, he changed physics, revolutionized civilization at the same time. So what this means is that here, the changing magnetic field makes an electric field. The electric field changing then makes a magnetic field, which then makes the electric field. And what we have is reinforcing undulations of the electric and magnetic fields into what we now call an electromagnetic wave. Now, we can use some of the constants here and determine the speed of those electromagnetic waves. And it turns out that that speed was exactly the same as the speed of light. Light was already understood to be wave-like in nature, but now we have a great unification of different phenomena. So these equations then are called Maxwell's equations. And this last term is an addition called the Ampere-Maxwell law, like so. And so what we have are different phenomena. So for instance, we have combing, let's say, a hair, and then picking up some bits of tissue, so like so. We also like to play with magnets. So here's a magnet like this, and like so. So then we have magnetic phenomena, and then we also have light. Very, very different phenomena now being explained by one overarching theory that we call Maxwell's equations. And so this was a great revolution in physics for unifying many different phenomena together under one umbrella. Revolutionized civilization because now we can have things like radio, and television, radar, and then with radio waves, microwaves, light waves through optical fibers, we can have cable coming into our house. We have the backbone with the internet through optical fibers, and we have cell phones. Anything that is called wireless depends upon these Maxwell's equations that we have here. Now, if we jump ahead about 44 years to 1905, just a tremendous year for Albert Einstein. At the age of 26, he was working as a clerk in a Swiss patent office and came out with 4 papers, each of which would be worthy of a Nobel Prize. One of them did, in fact, get the Nobel Prize, but not the one on relativity. That is what we're going to talk about here right now. Now, Einstein was a great fan of Maxwell and Maxwell's equations and studied those quite extensively. And Einstein came up with what we call a principle of relativity. This is not the theory of relativity, it's a principle. And that principle states that if we have an observer that is in uniform motion, constant speed, constant direction, no rotation, then they'll determine a set of laws of nature, laws of physics, and those laws will be exactly the same as any other observer going in any other uniform motion. So constant direction, constant speed, and no rotation. Every one of those observers will find exactly the same laws of physics. And in particular, they'll find the same laws that Maxwell has right here, and because then these electromagnetic waves travel at a certain velocity, that velocity is this part right here, which we also call the speed of light. Every one of these uniform observers, sometimes I'll call them uniform frames, will measure exactly the same speed of light, 299,792,458 meters per second. And well, by the way, this is 1 meter right here. And just imagine almost 300 million of these end to end to end to end. That's how far light will travel in 1 second. Or another way of looking at it is that imagine the distance that is equal to 7 times around the Earth. That's how far light will travel in 1 second. So it's tremendously fast. Now, Einstein was noted for the expression that imagination is more important than knowledge. Now, of course, he's not discounting the importance of knowledge. It is very important through Maxwell's equations. And however, he needs imagination then to determine what are the consequences of this principle of relativity and the speed of light being the value it is. And so that's where then he had to use his imagination to figure out then the logical, rigorous consequences of the things that he had postulated. So here then I'd like to demonstrate what some of those consequences are. So as an example here, let's suppose that this box contains an instrument for measuring the speed of light going into it. So let's say, for instance, so here's the light going into the box, and here then we'll open up the box, see what the speed is, and well, there it is, 299,792,458 meters per second. Now we can try this again. So we can have the box here stationary, and we can move the light in like so. And this box is measuring the speed, and the speed, well, again, is 299,792,458 meters per second. If we do this now, have the light close in, but move it away, like so. Again, the same speed as before. Now, astronomers encounter this phenomena quite frequently when they're observing distant galaxies. The further away the galaxy is, there's a greater redshift, which means it's moving away at a faster speed, just like I just showed you with the light moving away. And those light beams coming towards us from those very different galaxies are in fact coming at us at exactly the same speed as light from our own sun, reflected from the moon, out the window, and so forth. So we have the same speed measured in all of these cases. Now, let me show you something else. Just to reinforce the point, let's suppose that there's a car coming towards me at 60 miles an hour. From the other direction, another car coming towards me, also at 60 miles an hour. Now, I'll stand out of the way here. One car thinks that the other is moving towards it at a speed of, well, 120 miles an hour, just the sum of those two speeds. So let's try that here then. We've got a uniform frame here that's almost going at the speed of light. We have this light right here. Again, it's moving towards me at almost the same, almost at the speed of light. So again, I'll step out of the way, and now we have these two coming in. And again, the speed of light is measured to be this value right here. So even though this may be coming towards me at almost the speed of light, and this also towards me at almost the speed of light, the speed of light is still measured inside the box to be the same. So the idea here is that the speed of light, the speed of these electromagnetic waves, is really independent of what the source is doing. So we had the source as being the flashlight, but once these electromagnetic waves have been launched and the electric and magnetic fields undulating reinforce each other, that speed is then observed to be exactly the same, irregardless of how the observer measuring the speed or how the source is moving. And again, all of the assumptions here is that they're moving in relative motion, relative, uniform, constant speed, constant direction motion. Now, there's another illustration here. And that is a little bit more interesting, a little bit more complicated to show, but what I want to illustrate right here are in fact 4 perspectives. So I'm going to personalize it a little bit and say that we have an observer on the platform named Pat, so Pat on the platform. We have another observer in the train over here named Terry, so Terry in the train. And so what we'd like to be able to do is to look at what these observers are seeing. First of all, the first thing that Pat on the platform is going to do right here is then look at light. So for instance, I have a little light right there. If I turn it on, there it is. And so forth. So here we have the light that's turned on. Of course, when we turn on the light is then going out in all directions. Of course, I can see some, you can see some through the camera. Maybe there's some shadows on the walls or ceilings. But what I need to do then is to first focus on light only going in this one direction right here. That is along the direction of the tracks, which is of course the same as the direction as the train. We also need to slow down the light so that we can, well, pardon the pun, but see what's going on here in a little bit more careful and deliberate way. So what I'm going to do is I'm going to use these little guys right here and here, and these are going to represent the expanding wavefront of light, these electromagnetic waves. So as they're going out, this is where no light is, and this is where the light is turned on. This is again the outer edge of the wavefront of light as it's turned on here. So I'll just kind of illustrate that here. So we turn this on, and we see light then expanding out in both directions. Now Pat on the platform has measured a distance here, same distance over here, and so the speed of light in that direction should be the same as the speed of light in that direction. And so what should happen is that as the light turns on, we see that the light hits here and here at the same time. Now, of course, the picture is not exactly perfect. These guys don't move with exactly the same speed, but what I'm trying to do is illustrate the ideas. The speed of light the same in this direction, same as that direction. This distance is the same as that, so the light should hit the light switch here, or not the light indicator, as well as the shelter at the same time. Okay. Now what we're going to do next is we're going to visit Terry on the train, and so I'm going to get the train in position here. Now in all cases here, the train is truly an express train. It does not stop at the platform. It's just going to kind of keep on going. It is a uniform frame. It's going to move at a constant speed, a constant direction, and hence my track is a very linear track. So if we go ahead and turn that on, and I'll just move the train in position, and then what we'll do right here is this. Now, okay, so right here now, we're with Terry in the train. We're not moving inside the train. We're seated in our chairs, and we see the light go off. And again, by the idea that the speed of light is constant for all observers, we turn on the light like so, and there we see the light hitting the back and the front of the train at the same time. Okay, hopefully that makes perfect sense. Right here, this is the middle of the train. Sure, the engine's a little bit shorter than the cars, but nevertheless, what we have is the same distance here and here. Light expanding outwards, it travels at the same speed this way, same speed this way, and light should hit the front and the back at the same time. So this is us right here with Terry on the train. Now, what we're going to do next is very interesting. So again, I'm going to move the train back in position here. Okay, and so what we're going to do is we're going to be with Pat on the platform, and we're going to look to see what is light doing in the train as the train goes right on by. So what we'll do right here then is to put the train in motion, and then as the center of the train hits where the light is, okay, so then right about now. There's the light expanding out. Light hits the back of the train, then hits the front of the train. Now, just in case you missed that, let's try that one again, because this is very interesting and may seem a little bit contradictory to what we've just been talking about. So we'll repeat this demo, or you can go back and rewind or go back to the tape, but nevertheless, what we'll do is we'll have the train in motion, and as the center of the train gets aligned with the light right there, there goes the light. The light hits the back of the train, and then later hits the front of the train. Now, this is contrary to what we had said. If we were with Terry in the train, Terry would have said, no, the light hit the back of the train and the front of the train at the same time. Pat, looking at what's going on with the train, says, no, light hits the back of the train first and then the front of the train. So this is a seeming contradiction. Both views are right. Terry is right in saying that the light hits the front and the back at the same time. Pat is right in saying, no, light hits the back first, then the front. Okay. Now, I said that there were 4 perspectives, so that was the 3rd perspective. Now, the 4th perspective is this. What we're going to do is we're going to bring the train back, and we're going to be with Terry on the train, okay? And then we're going to look at Pat go by with the platform. So just imagine now you're on the express train and you're seeing the station. The station is then going by here. So let's see what happens here. So we are then, the train's coming along, we're with Terry on the train, and then here we have an alignment, and then I'll put these things out because what Terry is doing is looking at the platform, and then here the platform is moving, and so that light hits the signals, and then later hits that. So I can't quite coordinate everything as well as I'd like to, but let's try that one more time. Okay, so we're with Terry. Terry in the train is moving along, and then at this time when these are aligned, the light goes on. Terry sees the platform go. The light hits the signal, and then later hits the shelter. So Terry then again thinks that the light has hit both front and back at the same time, but Terry thinks the light has hit the signal first, and then later has hit the shelter. So we do have a little bit of a symmetry there. Each thinks the light for themselves, that is, Pat on the platform thinks light has gone the same distance in the same time. Terry inside the train thinks light has gone the same distance in the same time, but as Pat looks at Terry's train and sees what's going on there, light hits the first, the end, and then hits the front, and then Terry thinks, no, the light hit the signal first, and then the station. We've got 4 perspectives. They're all correct, but that's just part of this mystery of the special theory of relativity. Now, let me give you the answer as to why this thing works the way it does, and then we'll kind of go through step by step and show a little bit more details here. So first of all, what I'm going to do is I'm going to suppose that Pat on the platform has a series of clocks, and I'll illustrate those by this right here. So these are the various clocks that Pat has set up on the platform. Okay, so Pat has made sure that each one of these clocks is identical. They are all perfectly synchronized. They all click at exactly the same rate. And so Pat has made sure that at this particular time, that is when the train's coming by and it's aligned right here, that all of these clocks are reading, if you will, the 0 hour. Okay? And then Pat also has an ability to kind of look inside the train and see what's going on with Terry's clocks inside the train. Now, here's what Pat sees in terms of the clocks on the train. So Pat sees Terry's clocks. They don't look synchronized. Although Terry would agree that, yeah, all of her clocks are synchronized, Pat does not think so. Okay, it's a little bit of an interesting, what seems like contradiction there. So Pat has got all of the clocks here synchronized, and they're going at exactly the same rate. But as we look across and see what's going on with these clocks here on the train, Pat thinks that Terry's clocks are not synchronized. That this one runs a little bit in advance and this one's a little bit slow. Now, here, okay, we got some mathematics, I'm sorry to say here. We have this thing called the Lorentz transformation. Now, the Lorentz transformation turns out to be very important because if we look at Maxwell's equations remain the same if we go through this transformation. Let me describe what this is. If I think of x1 and t1 as corresponding to the platform, t1 is the time. So in this case, this would correspond to 0. And then x1 is the position on the platform as we move along. We're going to call this right here where the light is, we're going to call that 0. So this would be positive x, that would be negative x. Then what these equations then tell us would be here, what is the corresponding position that Terry sees in the train, and what kind of time does Terry see in the train? Now I'm not going to worry about this denominator for the time being. We'll get back to that a little bit later on. That's just an extra complication I don't want to get into at the moment. But the important point to make here is that the time seen on Terry's train here, that's the T2, depends not just on the time seen by Pat on the platform, but also on the position that Pat is then observing. So here now, because of that minus sign, what this means is that, okay, if T1 is 0, all of these are reading the 0 time, then T2 goes negative up here, and that's what we have. So this would be right there at 0. This would be a negative time. That would be like a little even more negative. And then if x1 is negative, going back this way, then here this quantity would be positive. So that's a little bit more positive, and that's even more positive. So this right here illustrating going from the platform to the train, going from x1 to x2, then this conforms to what we call the Lorentz transformation. Okay, now what I'll do right here next is to say, okay, now we've got the same similar situation if we are inside the train. Now, Terry, of course, has got all of the clocks here synchronized. They're exactly the same kind of clock. They tick at exactly the same rate, and Terry has them all synchronized. Then Terry looks at, well, what's going on in the platform? So what do these platform clocks now look like? And here they are. So here are the platform clocks, and then Terry is able to look across from the train over to various points on the platform and see, no, Pat thought Pat's clocks were all synchronized, but Terry disagrees. Terry thinks that no, these clocks are all different. And if we looked more closely at the Lorentz equations, we can find out that there's this consistency that we have here. So as the train is going this way with respect to the platform is moving that way with respect to the train. And the only difference between those two in terms of the Lorentz transformation is that the minus that is here in front of the V right here becomes negative. So this would be the platform moving with respect to the train. Then that minus V becomes a plus V. And so everything then does work out. So this is something that we'd like to explore just a little bit. So my next part is to demonstrate really what is happening here. And so what we'll do is we'll back up the train and kind of go through this step by step by step by step. And so here then we'll go to an earlier time. So this is on the platform. and this is on the train, like so. And then the light has yet to turn on, so we'll do this part right here. And let's get this back a little bit further, like so. Okay, so this is again from the perspective of Pat on the platform, looking at the clocks. These were all synchronized. Pat is then looking at Terry's clocks and saying, well, no, they look all a little bit off whack right here. Okay, so then what we'll do is we'll advance time just a little bit. So we'll move the train up somewhat here. So now on the platform, our time has increased by just a little bit here. And then on the train, here then like so, we see that, yeah, these have advanced, but we're not still synchronized here. So we do have these clocks that are a little bit off. Okay, then we'll go on to the next interval of time. So we'll move the train closer. So at this point, really should have this here and have this like so. So this is the situation that we had just looked at. The train's still in motion, but it's coming along, and now the light is going to turn on. Okay, so then our next frame, our next instant of time, we're doing this kind of thing here. So then this is on the platform, and this part is on the train. The light has already been in motion, and now, if you will, here we have this part, and this part for the light has come out so far. So the light now is right here at the end of the train and equal distance over here. So these are the various clocks that we see here. And we see that, over here, and we see that here the light has reached the end of the train when Terry's clock says this time that looks like it's 3 after. Now we'll continue on for a few more of these segments. Again, the light is going to go out further, and the train is going to go further. And so this is the train and its clocks here. And here is the platform. And so the light is still in progress. So we've got one leading edge here, the other leading edge is over here. And so then the train goes a little bit further. So this is the frame on the train right here, like so. And then we have the platform like this. The light has gone out even further here and over here. Okay. And so again, the time is advancing for all of them. And then what we'll have is frame number 8. This is on the train, so this is the train going out. Some more. Here's the light that's gone out here. And then our platform reads this. So time is still advancing. And notice here that at the front of the train, the time is almost at this 3 after. So if we go one more time interval, and then here, like so, and the light at this point should have reached the front of the train, and there it is. We see that now Terry's clock reads 3 after at the front of the train, just when the light now has come alongside of it. So this is the way that the Terry on the train can observe the clocks being the same. That is the same amount of time going from the front to the back, but it's at the expense of Pat thinking that these clocks are no longer synchronized. So the upshot to all of this is the following. It is that here now we no longer have a master clock of the universe. We no longer have a separation of space with its 3 dimensions like side to side, front to back, top to bottom, and clock just ticking away for everybody being the same. What we have is that now the time, the clock, is an integral part of the space itself. So we have this new entity called space-time, and the time for these observers can go differently depending upon their various motions. So this is a very interesting conclusion then that Einstein came up with based upon the Lorentz transformations and this principle of relativity. Now, if we're going to take a look at some other interesting phenomena, what I'd like to illustrate here then is the following. In order to measure a length, so if we have a meter stick that is in motion coming along here, okay, let's say it's part of what Terry's train involves. So then in order for us to measure this meter stick, what we would have to do as it's in motion is to make marks at the front and the back of the meter stick at the same time. Hopefully now that expression at the same time carries a lot more meaning to you, because here then what will happen is that as we look at Terry's meter stick going by, this is maybe what we see. Now Terry will look at that and say, no, that's not right. The meter stick is really this long, and what Pat on the platform had done is not put down marks at the same time. So if this meter stick is in motion, Terry will say, you put a mark here at the leading edge first, and then put a mark here at the trailing edge, and hence it looks like it's only this long instead. So Terry then looks at the meter stick on the train and says, no, it looks like this. Looks at what Pat says, no, Pat thinks it looks like this here. Now we can do the same experiment, that is, as well, Terry is going by, and Terry looks at what's going on the platform. The platform with respect to the train is moving this direction here to our left, and again what Terry would have to do is, well, with this meter stick, is make marks on the train, let's say, at the same time. This is what Terry determines. Okay, that's according to Terry's clocks, putting marks down at the same time. Pat, of course, on the other hand, thinks no, the meter stick is really this long instead. So Pat thinks that Terry did not, again, put marks down at the same time. So Pat thinks that Terry's meter sticks are shorter. Terry thinks that Pat's meter sticks are shorter. Who's right? Well, they both are. They both have their own correct perspectives on this. Now, another example of something that does happen here is this, with respect to time. I'm going to make a very interesting clock here, clock that's made out of 2 mirrors. And so what we'll do is we'll have, if you will, light that is pulsing back and forth here, back and forth, back and forth. So these mirrors are parallel with each other. And I'm going to suppose that the spacing is 1/2 of a meter, so that as light comes from the bottom to the top and reflects back down again, that is 1 full meter. And if we count this number's worth, this 299,792,458 round trips, that will correspond to 1 second. So if Pat is right here then on the platform, looking at the light bouncing back and forth, this clock can tick off seconds, just as well familiar as, well, as can be. However, Terry can have the same clock on the train, exactly the same spacing and so forth. Now the vertical distance right here, there's no disagreement about that, because if we have a vertical distance on the train, then as it goes by, let's say, a vertical scale on the platform, we see the top and bottom at the same time. There's no ambiguity there. And likewise, if we have something that's vertical on the platform, the train can see both top and bottom at exactly the same time. Same space, location, same time, so there's no misunderstanding about vertical distance. So now, Pat has a clock that is ticking off seconds. If we're with Terry on the train, we see exactly the same clock, not the same clock, but exactly like it, and it's counting off seconds. And if we're sitting in the coach with Terry, then we'll see this clock counting off seconds, just right. Again, the difference is that now when here the train is going by, okay, so as the train is going by, and I'll just mark with my finger, I'm going up and down with the finger. So this is Pat looking at then Terry's clock. What Pat will see is that the light is no longer going up and down, but is going on a diagonal because it's in motion. So look at my finger right here as it's bouncing back and forth. It's really, according to Pat, tracing out then more of a triangular shape. And because it's looking at a diagonal, that diagonal is longer than the vertical distance. That diagonal is no longer just a half of a meter, but more. Because the speed of light is always the same, then light has a longer distance to travel. Consequently, it will take longer for it to make one round trip. So Pat looks at Terry's clock on the train and thinks, Terry's clock is running slower, okay? Terry, on the other hand, thinks it's working just fine. Terry can look at then the clock on the platform. As the train goes by, the clock on the platform is going this way. And again, if I'm tracing out, going up and down like so, then Terry sees that the light on the platform is again going on a triangular form. And so again, Terry thinks that Pat's clock is running slow. Now these are special kind of clocks, but a lot of things can be thought of as clocks that are based upon the same fundamental laws of electrodynamics, electromechanics. And so here then, even though we have explicitly light bouncing back and forth, if we have, for instance, a wind-up clock, there are molecules that then interact through electromagnetism. If we have some quartz, again, those quartz crystals oscillate, again, based upon electromagnetism and so forth. So a lot of phenomena that we could use for counting time then are based upon, well, electromechanics or electromagnetism according to Maxwell's equations. So all kinds of clocks now should exhibit this phenomena. So Pat should look at every clock on Terry's train and thinks it runs slow. Terry should look at every clock on the platform and thinks those clocks run slow. We can have chemical clocks, and we can also have biological clocks. And so then, if you will, an aging process you can think of as a clock. So Pat looks at Terry on the train and thinks that Terry is aging more slowly than Pat. Pat is getting older quicker, according to Pat's perspective on the platform. Terry, on the other hand, looking at Pat, thinks that Pat is aging more slowly. So Terry then thinks that Terry's clock is aging or is going faster, and therefore Terry is aging more quickly. So we do actually have a little bit of a problem here. It's called the twin paradox. If Pat and Terry are twins, and they are together at the same age when the train and the light are aligned, then each thinks the other is aging more slowly. Who is right? They both are. We have one basic problem, and that is what we would like to be able to do is somehow get these two twins back together at the same place and time, and then make a comparison. Well, we might like to stop the Earth and then move the Earth back under the train, but that's really hard to do. So the best thing is maybe to have the train come to a stop and then reverse and go backwards so that then we can bring Terry back to where Pat is. But if we do that, if the train breaks really fast, then we have all kinds of interesting things happening inside the train. Backpacks will start flying to the front. Water bottles, cell phones, all then flying to the front of the train as it's braking. Hopefully, Terry and the passengers are not also flying to the front because they are buckled in with their seatbelts. This looks like then a new force has come into being. So no longer do we have a uniform moving frame, but now this frame is changing speed. It's no longer uniform, and as a result of changing speed, it looks like there's this new force. It acts very, very much like gravity. And as a matter of fact, as Einstein began to realize the equivalence between the effects of acceleration and gravity that he then developed the more general case of non-uniform moving frames. So all we've done so far is really to look at uniformly moving frames. We come to a paradox, but now to bring Terry back to where Pat is, we're going to have to look at a non-uniform moving frame. And that then involves what Einstein developed, what we call the general theory of relativity. And this looks at the equivalence of acceleration and gravity, and now forms the basic underlying principles for understanding gravity as well as the cosmos. Oh, by the way, to demonstrate the reality of this general theory, every time that you turn on your GPS system, it relies on the results of general relativity, because now our instruments are sensitive enough to pick up the time differences that general relativity tells us right here. I'll leave on one final thought, and that is this. Imagine a time and place where people thought that the earth was flat. And then let's suppose somebody has an insight that says, no, the earth is round. I can imagine all kinds of interesting conversations taking place as a result of the person with this insight trying to explain to others, the roundness of the world. How do you explain roundness to people who only understand flatness? It's very difficult, and some might not agree with it, some might not accept it. However, for those people that understand and accept the roundness, then understanding flatness is very easy, because then what we can do is we can look at a portion of what's round that is so small that the actual amount of curvature cannot be detected. And so then it looks or appears flat to us. So in this world of relativity, that is the round world, we're accustomed to a flat world because our realm of existence is really very, very small. In particular, our speeds are very small. The fastest that anybody ever really travels nowadays is, those astronauts on the International Space Station. They're going between, roughly 4 and 5 miles per second. And if we do a comparison here then with the Lorentz transformations, V would be 5 miles a second. C in the same units would be 186,000 miles per second. 5 divided by 186,000 is small. We square it, we get something really, really small. We subtract it from 1 and we get a number that is, virtually equal to 1. Take the square root. Again, this number is almost equal to 1. My calculator, as good as it is, was not able to determine this value right here when V was 5 miles a second. I had to go to a more sophisticated mathematics package in order to do that calculation. In short, an astronaut would have to be on the International Space Station for about 88 years in order to detect 1 second's difference between what their clocks would say and a clock on Earth. So I'll leave you with that, and then, at some later time, we'll have further discussion about gravity and the general theory of relativity. Thank you.